So one of the most convenient ways to describe or construct spaces is simplicial complexes. It's a purely combinatorial description, unlike CW complexes where we inductively had our continuous functions. So this generalizes the classical idea of defining graphs. So we wanted graphs here in a more general sense, allowing loops and multiple edges. But classically, you think of a graph as, well, let's make them straighter, as something where I have a bunch of vertices, and a pair of vertices either are connected by an edge or they're not connected by an edge. So it's an incidence matrix or an incidence relation which gives you what you would gives you a graph. Okay. Now there's a very natural way in which you generalize this. So suppose I take something with maybe a few more edges. So if I want to construct, say, a surface, a higher dimensional object, I can start with a graph, and then I can decide that certain triples of vertices bound triangles. Okay, it might look better unshaded. They bound triangles. And there has to be a consistency condition here. The consistency condition is that if 3 vertices bound a triangle, then every pair of these bound an edge. I mean, similarly, we can have tetrahedra, which are bounded by 4 vertices, and so on. Okay, so in general, we have what is called an n simplex, which is the set. We will not formally need this, but for now, so we can look at an n simplex. Delta n is going to be equal to the set of all coefficients. Let's call them a0 to an in Rn plus 1, with the condition that they're all greater than or equal to 0 and they sum to 1. Hence, they're all less than or equal to 1. 0 to n of ai is 1. Okay. So this is a convenient symmetric way of writing it. In the case of a edge interval, it's going to be written just like this. In the case of a 3 simplex, you will see a triangle in, I have a third axis going off this way, and then the picture doesn't become very clear, but it's something like this triangle here, yeah, which goes between vertices 1, this one will be z1, 0, 0, 1, and the x depends on how you have labeled your axis. So we are taking unit vectors and taking the span of these. These are one simplices, and we specify when things bound simplices. Okay. Of course, we will need edges not to intersect and various other such conditions, but this can be avoided by making a clean abstract definition. Okay, so you want an abstract simplicial complex. So this is simply saying that we have finite combinatorial data, which says when each vertex, also when a collection of vertices bounds a simplex. This has to be a non-empty collection, and there's this consistency condition that any face of a tetrahedron has to be a triangle, for example, and any edge of the triangle has to be a side. Okay. So we can simply define a simplicial complex. Okay, so a simplicial complex is a collection, so an abstract simplicial complex, sigma of finite non-empty sets. But for technical reasons, we'll have to say actually, let me not say actually, subsets of some set S. This is for the same reasons that in the case of groupoid we had to insist on being a small category. We make all sorts of constructions automatically which work only for sets. So you couldn't take all non-empty sets in the world or all sets of size 1 in the world. Let's ignore that. So we take a collection of finite non-empty sets such that if sigma is one of these sets and tau is a subset of sigma, then tau is also inside this simplex. This is just saying that, for example, the edge of a triangle, if 2 vertices, if 3 vertices bound a triangle, any pair of them bound an edge, etc. So this is a nice object which is completely abstract. And we look at some example. The simplest example here is, let's take the finite set. S is 0, 1, n, and I look at the power set of that. Okay, so this is the set 2 to the s. Okay, so this is the standard n simplex delta n. Later we'll see in what sense this is equal to this. But suppose we took 3 vertices. This is saying that every pair of vertices is joined by an edge, and the triple is joined by a triangle. And similarly, you'll get a tetrahedron, etc. So these are the standard simplices. Okay, but we look at a couple of more interesting examples, both from a geometric view as well as from other sources. Firstly, geometrically, suppose I had say an octahedron, which I'll maybe draw the middle part first. So here's an octahedron. We have a central square. We have a point not on it, and we connect that to all sides here. And similarly, we have a point below which we connect to all sides this way. Okay, it's not a great picture of an octahedron, but I think it's clear enough. This is simply made of triangles. On the other hand, if I had a cube is not made of triangles. I'll have to break it up into pieces to make triangles, right? So let's take a cube here. So this is the actual cube, at least to a topologist, it's a cube. It's not very symmetric. I'll have to break it. I'll have to add additional sides like this, lots of them, to make it into triangles, and then this becomes a simplicial complex as well. Okay. But there are a couple of examples which are important, which are not of a geometric nature a priori. And they are nice because you can start with an object from group theory or combinatorics, and in the first case, in the second case actually from topology, and get a simplicial complex associated to that. First is a Poset complex. So Poset means partially ordered set. Okay, so given, let's say, P, and with less than or equal to some relation, a partially ordered set. You let sigma is going to be the set subsets of P. Okay, so let's call them sigma contained in P. Sigma is what is called a chain. So sigma is totally ordered. With less than or equal to. Okay, so obvious example of partially ordered sets would be, for example, if I look at natural numbers and the order is not the usual one but x divides y, that would be a partially ordered set. Totally ordered are a sequence of numbers, and so you can order them so that each one divides the next one. It's actually a rather interesting example of a Poset complex. Okay, so here is example if I took p equals n and a is less than or equal to b if and only if a divides b. This is the definition. You get a rather interesting thing, and number theory is captured in the geometry of this complex. Okay, and if you restrict, so these are all, so sigma contained in P is non-empty. I have to restrict them to be non-empty. Subsets of totally ordered sets are totally ordered. So this satisfies the condition. And a second example is what we'll call a nerve complex, which in certain situations can be even nicer than the general case. So general case is, suppose we take X as a topological space, and we take U, which is some U alpha in A, as an open cover. Okay, so then the nerve complex N is going to be, I have to specify subsets. So I look at, so the vertices are going to be the sets in this open cover. So I look at collections of sets. I don't want them to be ordered. I look at collections of sets U1, Un. I'll just call them this, but maybe more accurately U alpha 1, U alpha n, such that their intersection is non-empty. Intersection U. This was U alpha n. Not alpha n, U alpha n is non-empty. Okay, here I have to assume that U alpha are not empty. So singletons are, so any of these collections, so this is non-empty collection of sets. Okay. And of course, if any collection is non-empty, then any subcollection is also non-empty. Intersection of a subcollection is also non-empty. Now, the reason this nerve is important is if further, so your typical open cover is by balls, and maybe locally balls in some nice curved space or whatever it is. So what happens is often enough, intersections of collections of open sets could be empty or non-empty, but wherever it's non-empty, it's contractible. If that happens, then the nerve has an associated topological space, because all simplicial complexes do, as we will see very soon. The nerve has, with its associated topological space, has the same homotopy type as X. So this is a way of combinatorially capturing a space in terms of a cover. So this is again a rather useful construction.